Hello, we are Group 5, and the theme of our presentation is data sharding. So currently, web application requirements increased a lot in scale. These applications' databases need to handle and store enormous amounts of data. Coping with all the traffic and data in these applications requires more resources. There are two ways we can handle this problem. We either scale vertically by increasing the performance of existing machines, or horizontally by adding more machines. Usually, the latter is preferred due to reduced costs. Now, after scaling out, we need to consider our data distribution model. We have replication and sharding. Replication is based on copying the same data to different machines. This is good to read data, but writing is more expensive, as now you need to write to every single node that has the data. In sharding, we split the same data into parts and store these parts in different machines. This is good for both reading and writing. However, sharding might not be the solution to every problem, and that is something that needs to be taken into account. There are multiple ways to accomplish sharding, but first we need to choose our partition strategy. This strategy is what is used to decide where we should put the data. In here, round robin is different from the other presented strategies because it does not require an attribute. In the round robin, we simply distribute each data into each machine, in the order of machines. When we reach the end, we go back to the first machine. This scheme is very simple and doesn't take into account what the data is and what its parts are. In the range-based approach, we need to use an attribute from the data, usually an ID. Then we give each machine a range. If the data attribute falls within a certain machine range, it will go to that machine. This is somewhat better than round robin because depending on the attribute, we could place data more carefully and evenly. The list-based approach is very similar. However, instead of ranges, each machine has a list of attributes it is responsible for. The final strategy, hash partitioning, is different from the previous ones in that a hashing function is used on the attribute key. Every machine is responsible for a part of the values, and if the hashed attribute falls in this part, it goes to the corresponding machine. This is better than the previous strategies because by hashing we remove bias from the data, and we are able to distribute data more evenly among the machines. So now we are faced with a problem, which is what is the attribute key that we will use? First, the attribute key should have a lot of different values. This guarantees that there will be fewer collisions. Another important thing we need to take into consideration is how users access data. Usually, they want the most recent data. However, choosing a chronological attribute, we might create hotspots in the data, because all of it would concentrate on a couple of specific machines and leave others with uneven load. Finally, related with user data access, we understand that user requests that share the same attribute key will hit the same node. Therefore, we must also take into care not to choose a key that might put excessive load on particular machines. In this brief summary of what sharding is, we conclude that the way we choose our data placement is important, as it can improve or degrade our application's performance. Sharding isn't always the best solution. If we need to access multiple shards to access a piece of data, we are increasing our communication overhead, and sharding should always ease parallelism and minimize our application's communication overhead. In the next topics, we will see real-world applications of data sharding.
Okay, so now we will talk about Accio. Well, Accio was created by Facebook, and it works as a locality manager, which means it is responsible for the placement and retrieval of data in Facebook's data centers. Now, the major contribution of Accio is the ushard, that represents the unit of storage in Accio, and we will discuss it more in depth ahead. So first off, why is it needed? Well, many of Facebook's applications have low read-write ratios, and this means that common practices like caching aren't very efficient because updates are happening all the time, and so caches need to be refreshed. Now, full replication is not an option because every data center would store the data, which would cause problems related to space and latency. It is, however, important to notice that the requests for some information are rarely evenly distributed geographically, meaning that most of the requests made for some piece of data are coming from the same general area, that being a country or a continent. Now, because of this information, Facebook knows that the data can be placed close to those requests for better latency, and then move it again if the demand changes. Now, when should we move the data? So there are two basic cases where this happens. And the first one happens when a user that typically uses Facebook from, let's say, Europe, travels to Asia and uses the application. Accio notices that the origin of requests has changed, and to improve user experience, moves the data to an Asian data center. The second and most common case has to do with the load each data center is under. So data can be moved to data centers where the traffic load is low, because, for example, it is night, and by doing so, removes some of the weight from the very popular data centers. Accio still tries to place the data as close as possible to the source of requests, so that the latency gain isn't that noticeable. So now the question is, what data should we move? And now we are going to discuss U-shards. So U-shards are an agglomeration of data that has some degree of connection. The logic behind this choice is that when we have to move some data, because, for example, the user is on a different continent, we want to move as much of important data at once as we can, so that the following requests by the user don't require communication with the faraway data center. Now, the fact that the shards aren't randomly created gives the system a performance boost that makes the transference of data much more efficient. These shards are relatively small, only about 200 kilobytes each, and the application is responsible for determining what pieces of information should be stored together. Now, to conclude this, we believe that Accio is an intelligent way of achieving good performance when dealing with large datasets that are spread across many data centers by combining the fine granularity of the shards with the relationship between the data they hold. We believe it is a very interesting solution to the problem of distributed low read-write ratio databases.
In this set of slides, I will talk about Google Spanner, a real-life database that employs sharding as a strategy to scale. Spanner was created by Google as an attempt to create a global distributed system that is cloud-based. It also is non-relational and scaled horizontally. So, how does it get values? Spanner uses queries to be able to get information to the user. The user creates a query that is compiled by the system into a relational algebra operator tree. The way the query gets developed into a tree is very important, because this tree can be divided into subqueries and be distributed, using the system coprocessors between shards, parallelizing the search in the shards and thus decreasing latency. Those subqueries are sent to the closest shards that have the information needed to create a response to that query, and in the end they send back that information to the main processor, and it's in its hands to recreate the original query. By having the original query tree as a blueprint, it can recreate the query with the received fragments and return the query response to the user. As expected, the system also has some problems. These here will cause problems in performance. A constant flow of data will make the system need to create more shards and restructure all the information it had before. Load balancing will make the system stop for a while and redistribute information in order to create a more balanced access between shards. That way it can use its parallelization capabilities to the maximum. Another problem are the possible faults in equipment. That will create the need to replace the equipment, and system-wise it will need to recreate and redistribute the shards. Now we will head to some system-specific problems. Sometimes the time making a tree for a subquery and get all the information needed takes more time than doing just the whole search. To solve this, it is needed to analyze the query size and evaluate if it's better to divide into subqueries or just do the whole search. The system also allows pessimistic search, in case it needs exclusivity in the shards. If there is a huge load of pessimistic searches, the system performance will degrade a lot, because of the logs spread across the shards. In the worst case, if something goes totally wrong in a query, the system will restart that query and redo all again. This is self-explanatory. To finish, talking about Spanner, we can say that it is one of a kind, real-life successful system that uses sharding to increase performance and is able to solve its problems, being a great example of a real-life sharding implementation.